this is what we were doing last class. We remember what these various statements are. Statement A says that computational problem P can be computed by a Java program. What we want to prove is that computational P is computed by a Turing machine. So that requires taking this Java program and compiling it into a Turing machine, right? So B says, well, problem P doesn't matter whether the input is read in as binary or ASCII. And C says any Java program can be simulated by a Turing machine. The running time just might go up by a square. All right, so those are our four statements, and our goal is to prove that A implies B implies C. And last class, we translated those four sentences into logic statements here, and so what we're gonna do is we're gonna go over these again, thinking about them as an oracle. The oracle, we want to prove A, B, and C implies Z, so the oracle is going to know A, B, and C, and then we're going to play the game to prove D. All right, so let's remember we're supposed to prove Z. So here, what's Z saying? Well, we prove it by the following game, right? Remember, I just added this in case people didn't read the previous slides. The prover constructs the exist statements, and the adversary constructs the for all statements. All right, so what do we need to do? It starts with an exist. So in order to prove that problem P is computable by a Turing machine, we have to we start by constructing the Turing machine. And then we're given an arbitrary binary string. And then we get to say what the running time of this Turing machine will be on this binary string. And then we have to prove that, in fact, the answer that our Turing machine gives on this input is the required answer for the problem. And we have to prove that the running time of this Turing machine on this input is, in fact, the running time that we claimed it is. Right? So everybody get this game? This is what we have to do. We have to do these things, right? But in order to help us, we're going to have some oracles, all right? So since we're assuming A, we're going to have Oracle A will help us. We'll have three oracles, Oracle A, Oracle B, and Oracle C. What will Oracle A do? Oracle A, we can give it, when there's a for all statement, if the oracle is assuring us that something is true for every object, then we can give the oracle our favorite object, and the oracle will assure us that, yes, it's true for this favorite object. And then when it's an exist statement, the oracle will provide us that object that is claimed to exist. All right, so here, if the oracle is assuring us A, then the oracle starts by, what's our statement again, right? The statement is saying problem P is computable by a Java program, right? That's what the oracle is assuring us. Sorry about that. So what the oracle going to start by doing, the oracle is going to start by giving us a Java program, right? Here's a Java program that I claim solves the problem. And then, right, it's a for all statement. So we get to come up with the input. The oracle is assuring us that this Java program works for every input. So we will give the oracle an input. And then it says exists time, so the oracle gets to come up with the time. The oracle will tell us, right? The oracle came up with the Java program, so the oracle gets to tell us what's the running time of this Java program on this input. So she gives us the running time. And then what will the oracle do? The oracle will assure us that the Java program on the given input gives the right answer for the given problem, and the oracle will assure us that the running time of the Java program on the input is the time that she said it was. Everybody get the oracle's job? It's pretty straightforward, right? All right, so now, right, we have to think about the one inputs in ASCII and the other inputs in binary, right? Remember, we're given the program B is given in binary and it outputs in ASCII. So here's what B says. We're gonna assume that B is true. What does B say? B says for our computational problem, it doesn't matter if you give it in a binary or give it in ASCII, it will give the same answer, right? So we're assuming that B is true, and our oracle will help us. How will our oracle help us? Well, it starts off with the for all binary string, right? So she's assuring us that something is true for every binary string. So so I'm going to give her some, right? Oh, so here I got ahead of myself. Here, it's true for every binary string. So I'm going to give her a binary string, right? And then what's she going to do? She's going to take the binary string that I gave her and going to convert it into an ASCII string, right? Here's binary to ASCII. And then she's going to assure us that the answer for our problem on the binary string is the same as the answer for our problem on the ASCII string, right? That the problem doesn't differentiate between them. Everybody get that? Now let's think about our compiler. Remember, our compiler takes a Java program and outputs a Turing machine. And if you're taking 2001, then you should know how to convert a Java program into a Turing machine. But I reassure everybody in this course, you don't need to know how to do it. You just have to believe it, right? So here's our statement. And what is the statement saying? It's saying every Java program can be simulated by a Turing machine, right? So we have some Oracle. We're assuming it's true. So we have Oracle C, which is going to assure us of that. It's going to help us with it. And as it goes, it says for all Java programs, all right? This Java program, Oracle C is assuring us that it's true for all Java programs. So we can give this Oracle our favorite Java program, right? If I have a Java program, I give it to the Oracle. And what will the Oracle do? The Oracle will feed it through this compiler and give me a Turing machine, right? The Turing machine that's stated to exist, right? Here C says there exists the Turing machine. She gives us this Turing machine, right? And as I said, we get it by running it through some compiler. Then the Oracle is assuring us that something is true for every binary string, right? So I get to give her any binary string I want. Here's a binary string. And what is she going to do? She's going to assure me that the Turing machine on the binary string gives the same answer as the Java program does on the ASCII string, right? Does that make sense? right? And I just got a little confused. Why is it say B when it's returning an ASCII string and not a binary string? And it's B because it comes from Oracle B. That's what the B is. It's B for the B statement. All right. She's also going to assure me something else. She's going to assure me that I can name any time. And if it happened to be the case that the Java program on this input takes T time, then the Turing machine on the corresponding input takes T squared time, right? She assures me of that as well, right? Everybody follow what this Oracle does, right? They're all pretty straightforward.
So that would be the big O time complexity?
Yeah, we're not doing big O because big O has this other for all exists stuff that's scary. So I'm telling you exactly the time is T, the time is T squared. But later on, we're going to get into big O notation. We just haven't done it yet.
Professor?
Yep.
Do we care about how the output is formed? So, because I know that we have the Turing machine with the regular input and then Turing machine with binary input. So
right. One might output binary and one might output ASCII.
Right, yeah.
You were so smart, I didn't think of that. But let's not worry about it.
Okay.
You know, you can either run that through a compiler, through a translator as well, or maybe the answer of the problem is yes, no, in which case it's not a problem. All right. Either way, I didn't think of it.
Or would we have like a base case where we just convert everything to binary automatically, regardless if it's binary or ASCII or whatever?
Yeah. Anyway, I'm just trying to have, you know, the uses of oracles here. So we can certainly improve on this. All right, so here's our statements, and our goal now. I'll try to. Did everybody get? I was talking a little fast. Should I slow down a little bit? We're going to prove.
Yeah, just a little.
We're going to assume A, B, and C is true, right? And we're going to prove Z. And we're going to just do it just like you think. We had these friends. Think about you have a friend A, B, and C sitting in your room. And you want to play the game Z between you're the prover and you're the adversary, right? We just do it in the obvious ways. All right? So we assume A, B, and C, and now we play the Z game. All right? So here I put these purple lines to say we're at the beginning of each of these statements, right? We're going to be moving left and right through these statements. And right now we're at the beginning. And right now our job is to produce a Turing machine, right? We want to prove that maybe it starts by the boss gives us a problem P, right? Because P is our free variable. So a boss gives us problem P. And now given P, our goal is to come up with a Turing machine that solves it, right? Now, how do we come up with a Turing machine? I can't write Turing machines, right? So we go over to our Oracle A, right? Oracle A is going to help us. And we can say, hey, Oracle A, can you give us a Java program, right? I don't know how to solve P, but you're promising me that P can be solved by a Java program, all right? So that would be a good start because I'm not smart enough to come up with a Turing machine to solve it, but you can come up with a Java program to solve it. So A, gives me a Java program, right? Now, what am I going to do with that Java program? I don't need a Java program. I need a Turing machine, right? So I go to my friend C because I know my friend C can compile Java programs into Turing machines. And C is saying something's true for every Java program, and now I have a Java program. So what do? I give my Java program, the Java program that A gave me, I give to C, right? So if C is true for every Java program, it's true for the Java program that A gave me, right? So then what does C do for me? C is really kind. C claims I gave C a Java program, and what does C give me back? C gives me back a Turing machine, right? C is assuring me that for every Java, there's a Turing machine. So I said, okay, for my Java program, give me the Turing machine that we're talking about, right? And she gives me this Turing machine M, right? Now, let's go back to what my goal is. My goal is to construct a Turing machine, right? And I just did it, right? I just constructed a Turing machine. How did I do it? I got a Java program from A. I gave it to C. C gave me a Turing machine, right? Everybody buy that? All right. So, and this is just a little aside here, right? Where did it come from? It came from this compiling. All right. So I moved all the, the purple things forward. Why? Because we had A did this, and now A's assuring us that the rest is true for the M in question, right? And C did this and this. So C is assuring us that the rest is true given the values in question, right? And we've come up with the machine, right? So that's why I moved the purple forward. All right. So what is our goal now? Our goal now is well, it's for all binary strings, for all binary inputs. So how do we prove it's true for all binary inputs? Well, we say, oh, let I prime be an arbitrary binary input. Now, we could just say, let it be arbitrary, or to make Jeff happy, we can put in the little story that where did it come from? It came from my adversary, right? This is some worst case binary input. And we want to, what do we want to prove? We want to prove that our Turing machine solves the problem on this worst case binary input. All right. So now I have a binary input. Well, what am I going to do with my binary input? Right? Well, I need to translate it into ASCII, right? So I give it to Oracle B. I take my Oracle B is assuring me that something is true for every binary string, right? And if it's true for every binary string, it's true for the binary string that the adversary gave me. So I give it to Oracle B. And what does Oracle B do for me? Oracle B translates it from a binary string into an ASCII string. And what do I do with this ASCII string? Well, hey, great. The ASCII string, now that I have an ASCII string, I can give it to A, right? Because what's A assuring me? A assuring me that for every ASCII string, her Java program gives the right answer. And if what she's saying is true for every ASCII string, it's true for the ASCII string that I got. Where did I get it from? The adversary gave me a binary string I converted into an ASCII string, right? So what she's saying must be true for this ASCII string, right? And then, so we gave it to her. Now let's go back to C, all right? C also has, C has a for all binary string, all right? So the adversary gave me a binary string. So I have a binary string, and the Oracle C's promising me that for every binary string, something is true, right? So, right, what she is assuring me is that the compiling works, right? A is assuring me that Java program works. C is assuring me that the compiling works, right? So I was given, let's review this. I was given a binary string from the adversary, which I converted into ASCII, right? Now I have the binaries version and the ASCII version of it. And what do I do with them? The ASCII version I give to A, and A will assure me that the Java program works on that input. And the binary version I give to C, and what will C do? C will assure me that the compiling works for that input. All right? All right, so now I moved all my lines forward, my purple lines, and what's the next thing I need to do in my game is I need to come up with a running time, right? Right, I was given by I came up with the Turing machine, and the adversary gave me an input, and now what do I have to do? I have to say how long the Turing machine will take on input I, right? So what do? Well, I need to come up with a time from somewhere, right? So I go up to A, and I say, A, you gave me a Java program. I gave you an ASCII string. You're promising me that there exists some time that that Java program takes on that ASCII string. Could you give that to me? And she says, great, no problem. Here it is, right? Right, so I can say, let T be the running time of the Java program that's stated to exist, right? She's promising me that it exists. She gives it to me, right? Does that make sense? And the way we write it in proof is we say, well, we know that this is A is saying that something exists. Let T be the thing that is stated to exist. All right? All right, then what do I do next? I'm given a T, so I come down here, and I know that if the Turing machine, if the Java program takes time T, then the Java time is T squared. So I take the T that the Oracle A gave me, the Java running time T, and I square it to get the Turing machine time, right? Everybody get that? So now I have the Turing machine time. So let's move our purple lines forward again, saying which things we've used already. And now our goal, what's my goal now? Is we've got all the objects we need. So now my goal is to prove that my Turing machine, right? Remember, I came up with the Turing machine, the adversary gave me an input. I need to prove that my Turing machine on the input the adversary gave me is in fact the required answer for the problem, right? How do I do that? Well, Oracle A, right? She came up with the Java program, and we gave her an input, and she's assuring us that the Java program on the input solves the required problem, right? So we know that this is true, right? This is the Java program. This is the ASCII input. It solves the right problem. What does B do for us? Remember, B assures us that the problem statement for ASCII inputs and for binary inputs is the same, right? So that gives B, tells us this relationship, right? And then what does the compiler assure us? The compiler assures us that for the Turing machine's output and the Java program's output are the same, right? So now we have these three statements, right? And if you follow them along, you can show that we get what we want. This is what we want. How do we do it? Well, Pi prime, here's Pi prime equals Pi, right? And Pi equals Mi, and Mi equals M prime I prime, right? See here, we just followed along. And so that gives us that yes, in fact, our Java program, or that gives us that yes, in fact, our Turing machine on our adversary's input gives the right answer. Are people following this?
Would you be able to just go back to the exist time T for A?
All right, exist time T. All right, well, this page, our goal our goal is to come up with the running time of the Turing machine, Turing machine, right? Now, what is A is assuring us? A is assuring us that she can give us a Java program such that any ASCII we give it, she can tell us what the running time of the Java program is, right?
Yeah, and then because of C.
Yeah, so she gives us the running time, and I take her running time. I mean, that's just a little note here. I take her running time of the Java program and I square it. Right? I didn't use anything over here. I just noted it. I just remembered that that was the case, right? This isn't being used. All I'm doing is I'm using this to get a time, and then I'm squaring it.
Well, why is it squared? What is the time of BTS?
Well, because we know that when we get there, that the compiler, what is the compiler promising us is that we give it a Java program, it will give us a Turing machine, right? It compiles some Java to Turing, and it's going to promise us that it solves the Turing machine solves the same problem as here's the Turing machine, here's the Java program. It assures us that the Turing machine gives us the same answer as the Java program, and it's also going to assure us that whatever time the Java program took, the Turing machine is going to take the square of the time. Right? So what do?
Well,
We're given the Java time, so we square it to get the Turing time.
but isn't the Turing time and the Java time the same thing?
No, because we don't want to get into Turing machines, but Turing machines have this head that have to zip back and forth, right? Every time it wants to look at a number, it has to zip back and forth, right? So that's why the time is higher.
Okay. Thank you.
Right?
So essentially, we just need to, like, because it's the Oracle that's telling us this, we're just saying, okay, it's true. So
Yeah.
for the compiler, it's just true that the Java program takes the time of the Turing machine squared, yes?
Yeah, I haven't used that yet.
Or
I
whatever.
haven't used C yet. Maybe I shouldn't have had a purple circle here. All I did, what I've done so far is I took the Java program, right? I took the Java time and I squared it, right? So let's move forward to this now, right? Now what do I have to prove? I have to prove that the time of the Turing machine on the input given to me by the adversary is the time that I came up with. Remember, I came up with the time. How did I come up with the time? I took the Java time and I squared it, right? Now I have to prove this, all right? So now let's move through the proof. How do we do it? Well, the Oracle A assures us that T is the running time of the Java program, right? So we know this. Then, what does Oracle C assure us? Oracle C doesn't know, right? Why do I have here for all time here? Because the Oracle C is kind of mechanical and stupid. The Oracle C is taking code for a Java program and it converts it into a Turing machine during sort of coding compile time, right? It doesn't run the program. So it doesn't know in some ways it doesn't know what the Java program does. It doesn't know what the Turing machine does. Line by line, it does a translation, right? So C is not claiming that it knows what the running time of either of these is, right? All it's claiming is if the Java program takes time t, then the Turing machine will take time t squared. right? That's what the compiler, that's what Oracle C is promising us, right? That's all Oracle C can promise us, because Oracle C hasn't actually studied the deep meaning of the Java program, the Turing machine, right? It just did a line-by-line translation. So what do we get from the Oracle C? What do we get from C? We get that for any time, if the Turing machine, if the Java program takes time t, then the Turing machine takes time t squared, right?
So this is we're actually now saying this part of A and this part of C like being used to prove that. Okay.
Yeah.
Whereas before it was like a comment.
Yeah, a thought, exactly.
Okay.
Right? Now we're actually trying to prove it. I mean, before we were kind of look ahead, so that we sort of chatted with with Oracle C on the side and said, hey, Oracle C, what's our running time going to be? And she said, hey, take the input and square it, right? Now we're actually doing the proof, right? So the proof, Oracle assures us of this, right? So everybody agree that Oracle A assured us of the Java program's running time. Oracle C is the compiler saying, hey, I took your Java program and I compiled it into a Turing machine, and I compiled it in such a way that the running time squares, right? That's what she promised us.
Jeff, do we need B Oracle here?
No, we use B Oracle already. B Oracle is about whether the problem had the, right? Does the problem translate from ASCII to binary? It doesn't say anything about running time.
Wait, so there's no B Oracle because in A and in C there doesn't exist, right? So we ask the Oracle for a Java machine, for a Java program in A, and for a time, and in C we ask it for a Turing machine, but in B there are no existential.
Yeah.
There's only for all, so we choose the for all.
Yeah.
So there's no Oracle there because of that.
All right, let's get back. Yeah, exactly. Let's get back to running time, right? What do we know about running time? From A and C, we know this and this. And what is our goal? Our goal is to give the running time of the Turing machine on our input. So what do we say? We say, well, if what the Oracle says, right here, if what the Oracle says is true for every t, it's true for the t that that A gave us, right? A gave us the actual running time of the Java program is t. And if what C is true for every t, then it's true for the t that we were given by the Java by Oracle A, right? So now what do we know? We know that if the Java program has time t, oh, well, look at Java program does have time t. Then our Turing machine has time t squared. Oh, great. That's fantastic, because I set t prime to be t squared. And so we're done. And that's the entire proof. Right? People buy that?
Okay, so basically what this is, right, is a different is similar to the games in that we play in the game between the adversary and the prover, except that we want to prove that it's true for sure, and the prover has assistance of an oracle and some other statements like A, B, C to help him prove that this is correct, right? And that's essential to do. Okay.
Yeah. Right? Isn't this fun, guys? I mean, it's sort of intuitive that if you knew A, B, and C, then you can prove Z. And this is just formally, right? Here's just it's an informal proof because we're doing Jeff's game. When we get to George's slide, we'll do a formal proof, which I promise you won't understand because I don't understand it, right? But this I understand, right? This perfectly makes sense. If I knew A, B, and C were true, if I had a friend promising me A and a friend promising me B and C, how would I prove Z? Right? This is how I would do it.
Can I ask you something?
Yeah.
So I noticed that you start with the A exists Java machine. Why did you start from there instead of starting from exists Turing machine? Like, how do you know where to start?
Well, that's actually an interesting question. And when I was writing this up, I actually wrote it up first, starting with A. It's a question of, do you do things in an order so that nobody waits, or do you do things on demand, right? Should A anticipate that you want a Java program, or should we play the game with Z and see what it is that we need, right? So the first time I was trying to prove these sorts of things, I was anticipating what we needed, and I started by the Oracle giving me a Java program. And what I found is that the students, it was more magical, right? The students were saying, well, why did you start with giving me a Java program? Why, right? So instead, I've decided to write up proofs as in, let's focus on the Z game, right? Because we know we need to play the Z game. So let's go way back. Boop, 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 boop. Right? So when I started by saying, what do I need? Right? So here's a paragraph starting, what I need is to construct M. And then I think, oh, well, how am I going to construct M? Well, who gives me, right? I can kind of come up here and think, who gives me M's? Well, oh, this guy, C gives me M's, right? But in order for C to give me an M, I have to give C a Java program first, right? Now, where am I going to get a Java program? Oh, A gives me a Java program, right? So now that's what I think. I needed Turing machine. So then I think it through, and then I say, so you might actually say, what's the first line of the proof? This is the first line of the proof, right? This is just a little discussion about the paragraph about what we're doing in the proof, right? This is just saying, what are we going to do in the next few lines of proof? What we're going to do is we're going to construct an M. But the very first line of the proof is actually the Oracle gives us a Java program. And then I use the Java program. I give it to the Java program I give the Java program to C, and C gives me a Turing machine, right? And then, right, so what's this paragraph doing? It's producing a Turing machine. And how does it do it? It does it through these steps. Did that answer your question about who goes first?
Yes.
Any more questions about this?
Sir, can we review when you prove P equals M, like M prime?
P.
When you,
sorry,
yeah.
which were we proving? P.
Yeah.
Oh,
yeah.
down here the. This what you want to prove?
Yeah.
All right. Well, here again, I did it kind of. I get people to help me on demand when I need it, right? So I think, what is my need? My need is that I need to prove that my Turing machine on the input given to me by my adversary solves the problem at hand. So I'm going to come up here and say, well, who's going to help me with that? Well, A is going to assure me that the Java program gets the right answer, right? So there it is. The A is assuring me that the Java program solves the problem, and B assures me that the problem doesn't care whether the input is binary or ASCII, right? So C assures me that. B assures me that. And what does C assure me? C assures me that when we compiled from the Java to the Turing machine, the simulation is correct. So whatever the Turing machine, whatever the Java does, the Turing machine is going to do the same thing, right? So those are three promises. right? And we combine those three promises to get what we want. And let's go through it. How do we get it? Well, here we start with the problem on the binary input. Well, the problem on the binary input we know is the same as the problem on the ASCII input, right? And then the problem on the ASCII input is the same as the Java program on the ASCII input. And we know that what the Java program does on the ASCII is the same as what the Turing machine does on the binary. So we combine those all and we get what we need. Did that answer your question?
Yeah, thank you.
Right? There's a lot of moving pieces here, right?
Jeff?
Yep.
For B oracle, why Pi prime equal Pi?
Pi prime equals Pi. Well, suppose P is the problem sorting, right? It's the computational problem sorting. And suppose I give sorting my input in binary. I give it a bunch of numbers, and those numbers are represented in binary. And somehow in binary, we distinguish one number from the next number. We encode the whole numbers we want to sort in binary, right? Well, we could also take the sorting problem and we give it the same input in ASCII, right? ASCII is characters 9, 8, 7, right?
Yeah.
And this is just saying, when I'm sorting, I don't care whether you give it in binary or you give it to me in ASCII. I don't care.
Oh, I got it.
Right?
Yeah.
So does it mean that B works either way? It's like from binary to ASCII and from ASCII to...
Yeah,
okay.
yeah. We could have written B. This says for every binary string, it does the same for the ASCII version, but we could have converted the other way. We would have to then say, yes, this is a one-to-one mapping, which we haven't quite said here, but sure. And actually, maybe it's not a one-to-one mapping. There might be some binary strings that aren't actually ASCII, right? They're just faulty binary strings.
So how to reassure that the function is one-to-one?
Well, in fact, I'm going to claim we don't even care, right? Because suppose the adversary gave us a binary string that's not proper ASCII, right? Well, then the problem is going to say, hey, I don't like that. It's not proper ASCII. So the problem will say, hey, this input's of the wrong format. And hopefully our Turing machine will say, hey, this input's of the wrong format. And we'll be right.
Okay, I see.
Right. Everybody see how we're doing this? And the question.
Can I say something?
Yeah.
Yeah, so like for example, if you say like, if you're given like oracles and you say like, for example, like so prove that Pi is equal to M, like Pi prime is equal to M prime I, then we would have to do those list or oracle and all the steps that we have to assure to get to come. Yeah. Same thing.
How do I know this is true? I mean, you just think, I say intuition's good, right? You think intuition. How do I know that my Turing machine solved the problem? Well, I knew the Java program solved the problem. I know that the problem doesn't care about ASCII versus binary, and I know that my compiler worked correctly, right? That's how intuitively I know my Turing machine gives the right answer.
Yeah, so like specifically on intensity, would state specifically like there's a combining gives that you want us to yeah.
Right.
Okay.
So if we were taking 2001, what would we spend our whole time doing? We would be spending the time proving C. we would be proving that you give me a Java program, I can convert it into a Turing machine, and they would do the same things. And I would also prove that the running time squares, right? That's C is what we're going to prove in 2001. And then I'm just expecting that you are smart enough that you then know that if a Java program can do it, a Turing machine can do it, right? But this is just saying, oh, how do I know that? How do I know that? And well, intuitively, we just say, hey, this is what we're doing, right? In 2001, I wouldn't even go over this proof. I would just say it's obvious. I wouldn't even mention binary for ASCII at all, right? That would just get slumped under the rug without any mention of it whatsoever. And the fact that a Java program can do it, then a Turing machine can do it, I would just bang. I would just say, hey, it's true, right? In fact, I think.
And well,
right. In fact, this is what I would do in 2001, right? I would say, look it, if a Turing machine can do it, bang, a Java program can do it, right? I would say, hey, the definition of computable, it doesn't matter if you define computable by it's what can be done by a Turing machine or what can be done by a Java program. It's the same, right?
But the opposite doesn't like it. If you can't say that if a Turing machine can do it, a Java program can do it, because we can't say the opposite though.
No, you're you're absolutely right. We can't say the opposite. In order to say the opposite, we have to, and another thing that we do in 2001 is I prove you give me a Turing machine, then I can write a Java program that simulates it, right? And when we do that in 2001, we do it very, very, very fast, right? Because, well, come on, you guys are Java writers. If I give you a Turing machine, what does a Turing machine do? It moves its head left to right, it changes state. Come on, you could write a Java program that simulated that, right?
Right.
So in 2001, I might just say it, well, this is obvious, while I give a lot more time converting from a Java, right? This Java program, it has while loops and it has function calls, it has a stack, right? In fact, we didn't even do the whole conversion in 2001, right? We kind of did simple loop goes to, right? I guess what we said is you take a Java program, you compile it, right? What is a compiler? You have a compiler in your desk that compiles it into machine code, right? And then in 2001, we said, well, if a compiler, if machine code can do it, then a Turing machine can do it. Right?
Right.
But everybody good with this? This is the end of these sections, right? We're now, look at this. Oh, here's just some more practice things. Oh, this is me doing the exact same thing a billion years ago. And you can look at this proof and see how it differs. But we don't need to do two. And you can tell me which proof you like better, right?
This is like an automata mod, like because S1, S2, you know, you're listing. I can see.
Here I have S1 is the first statement and S2 is the second statement. And we're trying to prove that S2 implies S1. Right? And more or less it's the same proof. So if you want to see how to write it up on a test more, right, then maybe you can read this. All right. Any questions?
So like for the test, we add the message.
So on a test, I can tell you question 4, which if I delete question 2, then it'll be question 3, right? Question, the last question will have 4 examples. Did you mute yourself? All right, maybe it's done. Oh, there, I just muted everybody, so don't take it personally. If you want to unmute yourself, you can unmute yourself. Hopefully I'm unmuted. Can you hear me still?
Yes.
Yeah, okay, good.
Yeah.
All right, so the last question, there are going to be 4 parts, and each part will say, here's some for all exist statement. If it's true, then this other for all statement is true. And you have to prove the right-hand statement by using the left-hand statement as an oracle. All right?
Mm-hmm.
And it's my opinion that each of them is trivially easy. But if it turns out that the average is low, then that's good, because right now the average is too high.
Professor, could you
Yes.
just show us how to properly write out the answer? Because I know you explained it well, and it's one thing if we understand it, but I feel like, at least for me, actually writing it out on paper like a proper proof, or even like your version of a proof.
Right. Right.
So,
well, and somewhat, I think I did here. I mean, what would I say here? I kind of like what I wrote here, right? Look what I wrote. I said my goal is to prove Z. So how do I prove Z? Right? I'm going to prove Z by playing the game, right? So what do I have to do? Oh, here, we're too far ahead.
So can we talk about playing games in the test? I mean,
yeah, this is an informal. Yes. No, it's not that you can talk about games in the test. You have to. This is the way I want you to prove it. All right. So, where am I? All right. So here, this is what would I if this was the question, right? If my question was given A, B, and C, prove Z, what would I want you to write? I would write, well, I want to prove ABC gives me Z, so I assume ABC, and now I'm going to prove Z by playing the game, right? Okay, the first thing I need to do when playing the game is I need to construct an M. All right, so how do I construct an M? Well, I go over to the oracle and I say, the oracle C tells me that C is true for every M, so it's true for my M in question, right? And then, right, so that's, right, so, here, sorry, I skipped something.
yes,
sorry, I need to construct a Turing machine. So what do I do? Oracle A tells me that there exists a Turing machine. Oh, sorry, there exists a Java program. So what do I say? I say, let M be the Java program stated to exist, right? I mean, that's not, I mean, I want you to see that I'm bringing in personalities, oracles and stuff, but if you don't like my hairy-fairy stories, what I'm writing here is pretty concrete proof, right? What the concrete proof is saying, I'm assuming that A is true. What's A saying? A saying that there exists a Java program. So what's my first line of my proof? Is let M be the Java program that's stated to exist, right? If I told you that there exists a something, then your line of the proof can say, let X be the something that is stated to exist, right? And then, what's my next line of my code? My next line code says that C is promising me that something is true for every Java program. I have a Java program. Hence, C is assuring me that it's true for that Java program. So here, what do I write in my proof? I say C is true for every M, and hence it's true for the M that I have, right?
Mm-hmm.
And you'll note every object as it comes and goes, you might want to give it a different name. right? So I didn't completely give things different names. I also gave them different names by different colors, right? This M is a for all green M, and this is there exists a yellow M, right? And so if when you're writing it up, I would have this yellow M and this green M have different names, right? I mean, I have them different names by having them in color coordinated, and if you can't do colors, then give them different names. And so then here there exists the yellow M. So now I have something that I'm calling yellow M sub-exists maybe, right? And what am I doing with that yellow M sub-exists? I'm saying, hey, Java, C says that something's true for all green M. So let green M be yellow M, right? And now from now on, my green M is yellow M, right? And then what does C say? C says, right, here we
There
C
exists a
says
turing
that
machine.
there exists, oh, here's my next line, right? I need to come up with a Turing machine. So what am I going to do? I'm going to say, now C promises me that something exists, right? So let M prime, let the orange M prime be the green M prime that's stated to exist. Right? Are people following that? I think this is a perfectly reasonable thing that you could write. Right? Are people getting this?
So you went from the exist Java machine to all Java machine, right?
Yeah, well,
Can you go back from like all Java machine to exist Java machine?
well, no, I'm assuring that A and C are true, right? I have an oracle that assures me of A, and I have an oracle that assures me of C. So the A oracle gives me a Java program, and then the C oracle takes my Java program and gives me a Turing machine. Now, you might be confused. It's harder because we have an A, B, and a C, right? In what you're doing, there won't be an A, B, and a C. There'll only be an A, right? Given A, you have to prove Z. So maybe what